types. So for instance, when it comes to thinking about numbers, computers usually have a different way of storing whether something is an integer, like 1, 2, 3, 4, 5, or 0, or negative, negative 1, is an. All right, hello everyone, welcome to our next computing-focused mathematics section that we're going to talk about. And this is going to be basically using the same things we talked about over the last few sections here, but specifically focused on applications of binary and hexadecimal. Because remember, in computing, when it comes down to it, everything is stored in binary, and sometimes accessed using hexadecimal for programming purposes. I will mention here, a lot of details of some of this stuff is going to be specific to programming language, but one of the things that is important to know about computers is that data is stored according to different types. So for instance, when it comes to thinking about numbers, computers usually have a different way of storing whether something is an integer, like 1, 2, 3, 4, 5, or 0, or negative, negative 1, negative 2, negative 3, etc. That's one type of data. You also have data that stores like a decimal value, and then you also have things like characters. So when we're representing the letters on our keyboard or whatever it is that we're using to type out our password, that is represented as its own sort of data type. And each data type requires a certain amount of storage space, and using different amounts of storage space will allow us to do different things in a way that is very, very important to actually understand some of the underlying math, because it gives rise to some interesting phenomena and potential problems. So in digital music, this is something that's near and dear to my heart, because I do, as you can probably tell, I do some music things, I do my own recording sometimes, and in music software, we have what's called pan. So you might notice this when you're listening to music, that some things come out of one side of the speaker and some things come out of the other side of the speaker. That piece of information is stored digitally in the computer as a 1-byte integer. So remember again, integer, like we said, positive or negative whole number, as well as the 0. And the specific way that computers store integers is that half of the values are going to be negative and the other half are going to be positive. So that's going to include 0, by the way. So if we first want to answer this question, how many different numbers are we using to store pan values? Well, we have to remember what a byte is, right? So remember that 1 byte is 8 bits. So if we allow ourselves an 8-bit integer, that means we have 8 different spots to store either a 1 or a 0. So 1, 2, 3, 4, 5, 6, 7, 8, right? Remember that in binary, each digit can be either 0 or 1. So I've got 8 different possibilities here. That means all in all, I'm going to have 2 to the 8 possible different values that can get stored here. So this is going to be 2 to the 8. If you'll recall from the previous section, we saw that 2 to the 8 equaled 256. So there's 256 different possibilities for how far to the left or to the right. Now, with these pan values, they're actually stored as an integer that can either be positive or negative. Now, if we were to consider just positive values, so if we just wanted to note positive values, giving ourselves 256 different possibilities, well, I should say just positive or 0, if we start counting at 0, we could go up to 255, right? We have to count to 1 less than the number if we start counting at 0. But now, with possible pan values, half of these are going to be negative, and half of them are going to be positive. And here, because of the way that this will make sense, we can talk about this in a little bit more detail in a second, but if we include 0 in our positive numbers, we got 256 different values that we can store for this pan. So half of them are going to be negative. That's 128. Half of them are going to be positive, but that half is also going to include 0. The reason why we start with 0 is because if we want to have all zeros, we talked about this before, right? Having all zeros is going to store this as the number 0. And then we'll count 1, and then the next one's going to have to be 1, 0, right? And then 1, 1, and then the next one resets, 1, 0, 0, and so on. So we will count up all of that way. If we keep counting, we're going to get as high as we can possibly count. So how high could we get up? So if we kept counting like that, if we were to get to 7 of these things here, right? If we had a 1, 1, 1, 1, 1, 1, 1, let's remind ourselves how big that is in binary. So if I counted all this way up here, remember how we count this in our place value expansion, this would be worth 1, that's worth 2, that's worth 4, 8, 16, 32, and then 64. If you add all of this stuff up together, plus that, plus that, plus that, plus that, plus that, plus that, it will be worth 127. So the positive values are going to go from 0 all the way up to 127. Again, 0 is not technically positive, but that's where we start counting. Now the negative values, the way that integers get stored is that if the first digit is 1, then it's going to be negative. So if that first digit gets marked as 1, here's the weird thing. Once we get to that thing, we're going to go all the way back to the most negative that we can get. Just so that way, each time we start counting again, it ends up increasing it. But it's a weird thing that happens when we get to the maximum value. It's going to reset there once that first digit becomes negative. So the negative values are going to go from negative 128 up to negative 1. So all in all, when you're storing the pan value in a digital music system, it's going to go from negative 128 all the way up through positive 127. I, for the life of me, could not figure out when I was first using the software why it went down to negative 128, but only to 127, until I understood exactly how that number was being stored. Now, in order to store this 8-digit, or excuse me, 8-bit or 8 binary digit number, we use 1 byte, which requires 8 binary numerals, as we just mentioned. Let's recall how this translates to hexadecimal. Remember that each hexadecimal digit, from what we talked about in our hexadecimal section, and when we converted it to binary, each hexadecimal digit represented 4 binary digits. So now if I have 8 binary digits, which I do with an 8-bit integer here, so 8 bits, so since 4 requires, or translates to 1 hexadecimal digit, 8 bits will require 2 hexadecimal digits. Now, a 1-byte integer is useful for describing something like pan, because we can describe a whole pretty big wide range of values on the right side of the speaker or on the left side of the speaker. But in practical purposes, there's a lot of scenarios where that number is simply not big enough. So in a lot of computing languages, integers are typically stored with considerably more data. So often stored either as 4 bytes or as 8 bytes. So let's ask ourselves, for the 4-byte case, how many different decimal numbers can we store as a 4-byte integer? So we first have to remember that 4 bytes, each byte is 8 bits. So taking 4 times 8 means that 4 bytes will translate into 32 bits. So this is often called, another way of saying this is a 32-bit integer. So if I have a 32-bit integer, how many different possibilities do we have? Well, just like the math we talked about above here, if I have n bits of storage, the number of different possible numbers I have is going to be 2 to that value. So we take 2 to the 32. We're going to get a really honking big number out of this. 2 to the power of 32 is, goodness me, 4294967, okay, so that is going to equate to a little bit over 4 billion. But now, like we mentioned above, when it comes to storing a value as an integer, half of these values are going to get counted as positive, that would include 0, and half of them are going to get counted as negative. So let's think about how big each of those halves is. If I take that value and divide it by 2, I'm going to get 2 billion and change. So 2, 147, 483, 648. So that was the result. Above, by 2, divided by 2. So like we saw with the 1 byte integer, or the 8-bit integer, half of those values got counted as negative. So that means when we're counting the decimal range, the most negative it can get is going to start with that negative 2,147,483,648. And now this is going to go up to almost the same number positive, but not quite, right? So we have one fewer number that's going to be positive here, because the principle of counting is going to work out exactly the same. So it's going to be one less than this. So 2,147,483,647. So if we are storing something as a 32-bit integer, we can get anything in this range. Let's ask that same question like we did, but above, how many hexadecimal numerals are required to store a 4-byte integer? Well, again, we can note that 1 byte corresponds to, like we said up here, 2 hexadecimal digits. So then 4 bytes is going to be 4 times as big, so that's going to require 8 hexadecimal digits. So actually, even though it requires a whole bunch, it looks like it requires, what, 10 different decimal digits. It actually only requires 8 hexadecimal digits to represent that. And now this might seem like kind of weird and arbitrary, but it turns out that this has some pretty serious real-world consequences, knowing these values, or at least knowing approximately these values. Because you might think that 2 billion and change would be enough to do whatever it is that you want. Turns out that that's not actually always the case. So for instance, there was a problem with the video, you may have heard it, called Gangnam Style. And Gangnam Style was the most popular YouTube video. And in fact, it actually got past this number. And YouTube at the time stored things as 32-bit integers, so it only stored them as that number. Meaning once it got past that, it said that Gangnam Style had negative 2 billion and change views. And because of that issue, it forced YouTube to completely overhaul how they were storing integers. There's another issue, which is called the year 2038 problem. I'll provide a little link to it in Canvas. We can actually explore it a little bit more. But the year 2038 problem has to do with a particular phenomenon called Unix time. And in Unix time, time is getting stored as one of these integers. The problem is, this same phenomenon is going to happen in Unix time. And that will happen at some point in the year 2038. And when it does, it's a potential issue. So I'll just leave it at that for right now. But what we can do now is we can explore a few more applications to this. So again, different ways that we can store information here. So one thing that gets recorded in, say, a video game system is you've got different pixels represented on the screen. So in 16-bit, the color of each pixel can be stored as a 16-bit integer. And this is sometimes called high color. We could ask how many different colors can we represent using 16 bits. It's going to work basically the same as we just did a moment ago. If we have 16 bits, each of those can be either 0 or 1. So that results in 2 to the 16 different possibilities. If we do that, we get 65,536 possibilities to represent that many different colors. It turns out that the human eye can actually represent quite a bit more than that. We can process perhaps upwards of around 10 million different colors. And the way that a lot of computers do, and this actually varies quite a bit. I got a little lost in the Wikipedia article for a moment on some of this stuff, but oftentimes the way that we represent colors in digital computing is using what's called true color, otherwise known as RGB. So an RGB value, you may have encountered this already if you've done some programming, but an RGB value is a triple of numbers, red, blue, and green. And those different values are going to indicate the respective intensity of color saturation of the color red, the color green, and the color blue. So the saturation of each of those colors is going to be recorded using 1 byte. And we mentioned on the previous page, if we use a 1 byte integer to store that value, it's going to be something in between 0 and 255. But in the interest of compactness, these numbers are written using hexadecimal. And you can check out, it's very easy to find an RGB generator, an RGB table. Here's one example of it. You can see that in the PDF or document version of the notes here. But I found an interesting color. Some might say a terrible color, but the shade of seafoam green is recorded as this thing, so that little pound sign is part of the notation to indicate that it is a hexadecimal number representing the RGB value. And what I want us to do is practice our skills from a previous section and convert each of these color values into a decimal between 0 and 255. So really the main thing is just to note that in hexadecimal, or rather, excuse me, in the RGB system, each of those 2 hexadecimal digits corresponds to 1 byte. We noted that on the previous page, right? So these 2 digits here are representing the red, the next 2 digits represent the green, and then the last 2 digits represent the blue. So let's do each of those one by one. The red saturation here is going to be the number 93, but remember, it's not 93. That is 93 in hexadecimal. So remember the way that we do this with a base expansion is that first digit 9 is actually worth 16 times its value. And then we will add to that the value here, which is 3. If we do out that calculation, 9 times 16 is 144. Add 3, we get 147. Again, remember that's in base 10. What about green? Well, the second 2 digits represent the green saturation, so that's E9 in base 16. Remember with hexadecimal, once we get to 10, we start using the letter A. So then B is 11, C is 12, D is 13, E is 14. So that first digit is 14 times the base 16, and we will add to that the value 9. Unsurprisingly, seafoam green scores pretty high on the green rate, 233. So really close to its maximum value. Last thing is our saturation for blue. So blue here for this particular shade of seafoam is given as BE. Well, as we mentioned, A is 10, B is 11. So that first digit, is going to be 11 times 16 will be its value, and then E, we said, had the value of 14. So when we combine these, 11 times 16 plus 14 works out to be 190. So this is one way we have to represent RGB. Another thing that gets talked about in this context is what we call the percentage saturation of a color. So the percentage saturation is going to be the fraction of its maximal value for each of those colors, red, green, and blue, written as a percentage. This is actually something that has really nothing to do with binary or hexadecimal, but it is an application of percentages that we've seen before. If we want to describe the percentage saturation of a color, we have to think, what is its maximum value? We can note here, the minimum value is 0, and the maximum value is going to be 255. That is as intense as the saturation can get. So having noted that, our saturation for red is going to be 147 over 255. And these are just regular decimal numbers that we're working with here, so I can just tell my calculator to do this stuff. Right, our calculators are programmed for decimal, even though they're programmed in binary. Kind of weird. But if we do that, we get 0.576. Remember, what we were trying to do is express this as a percentage, so let's multiply that value by 100, and it says round to 1 decimal, so this would be 57.6%. So actually the seafoam green, this particular shade of seafoam green, actually has quite a bit of red in it. Now the green value, we're going to take that decimal value of the saturation for green divided out of the maximum that it possibly could be, 233 divided by 255, we will get 91.4%. So pretty much as green can be. Lastly, for blue, we're going to take 190, we computed above, divide that by its maximum possible saturation, which is 255. Oops, let me try that again. There we go. And again, if you want, you can multiply that by 100 to see it more easily as a decimal, sorry, as a percentage, excuse me. So if we round that now to the tenths place of the percentage, we will get 74.5%, which is to say that seafoam green has a lot of blue to it as well. Last question we can ask here, we saw that with high color in a 16-bit system, we could represent like 65,000 colors. What about if we use this true color system? Well, let's note, again, each color is going to be 1 byte, as we noted, which is equal to 8 bits. And from the last couple of examples we've seen, 8 bits gives rise to 2 to the 8th possibilities. So that means there's going to be 2 to the 8th possibilities for red, 2 to the 8th possibilities for green, and 2 to the 8th possibilities for blue. And every single one of those red possibilities is associated with whichever of those green and whichever of those blue. So when we put all of this together, we're going to have 2 to the 8th possibilities for red, and then 2 to the 8th possibilities for green on top of that, and then another 2 to the 8th possibilities for blue on top of that. So we're going to record this as 2 to the 8th times 2 to the 8th times 2 to the 8th. If we think about our exponent rules, right, we add these exponents. This is the same thing as 2 to the 24th. If we take 2 to the 24th power, in other words, if we use a 24-bit number to store this, we have, let's see what this is, 167777216. So that is to say 16 million different possibilities for color. Again, like I said, it can actually get more complicated than this for storing color. Like apparently Photoshop uses even more colors than this because of a lot of technical reasons that I don't fully understand, but I encourage you to check them out if you're curious. All right, so one last example, and you'll see some similar examples to this next thing in the homework, which is another important thing for understanding how data is stored in a computer. And there is this code that is called ASCII. Again, if you've done your own programming before, you don't need me to tell you about ASCII. In fact, you might even know more about it than I do. But in ASCII, we use a decimal number between 0 and 127 for each character on a computer keyboard. In fact, if you go beyond that, you can use the next numbers to store special characters, like, for instance, letters that have accent marks, for like Spanish or French, for instance. So, but the ASCII code is this standardized system that makes it so that every computer, more or less, understands how to process binary and translate it into text that we can read. So when we press a key on our keyboard, the computer is going to convert that character into an 8-bit binary number. And there's some standard ways to do this. The ASCII code for the character capital A is 65. Let's remember how 65 gets stored in binary. So 65 in binary, if we wanted to convert that, remember we thought about this process as like making change, right? So if we only allowed coins that were powers of 2, what coins would we need? We would need a 64 and then 1, right? What is 64 in binary? Well, that's 2 to the 6th. So that would be if we had 1 and then 0, 0, 0, 0, 0. Let's double check here. I think I need one more, right? So that would be 0. So that would be the 1's place, 2's place, 4's place, 8, 16, 32, 64. There we go. So 64 is this in binary. If we add 1, 1 in binary is the easiest, or perhaps the second easiest after 0. If we add these two things together, we will get a 1, a bunch of zeros, and then another 1. Now, since this gets stored as an 8-bit binary number, 1 byte, that gets stored as that number we just see here, 0, 1, 0, 0, 0, 0, 0, 1. Then the next letter in this capital B is going to be the next number. Let's find the binary code for that letter. So capital B is going to be 1 larger than this right here. So we're going to we need to find the number after 0, 1, 0, 0, 0, 0, 0, 1. Well, if we add 1 to this value, when we count in binary, adding 1 to this is going to cause us to carry the 1. Let's see that. 0, 1, 0, 0, 0, 0, 0, 1. If we add 1 to this, I can just write it as plus 1. I don't need to write the zeros in front of it because they don't do anything. But if I add 1 to 1, remember I can't write 2. So what I have to do is put a 0 down here and carry the 1. And then 1 plus 0 will be 1, 0, 0. And then all these other digits are going to be the same. So that's how we write capital B in binary. This is how, when a computer sees this and knows that the data is a character, it's going to represent that using the letter capital B. What about for hexadecimal? Remember the way that we convert between binary and hexadecimal is we're going to chunk this thing up into 2 4-digit binary numbers, each of which is going to translate into a hexadecimal numeral. And you can, if you like, go to the table that we discussed in the previous section and convert using that, or we can observe, think about what this works out to be in decimal, right? So this number here, 0010, is going to equal 2, right? So think about your decimal place. That one's 1, that one's 2, that one's 4, that one's 8. So this is going to equal 2. Well, 2 in hexadecimal is pretty easy. It's 2. Same thing, 0, 1, 0, 0, that first digit here, so I'm going kind of right to left here. In binary, that's worth itself times 2, that's worth itself times 4, so that's worth 4. So that digit's 4 in hexadecimal, that digit is 2 in hexadecimal, but again, when we're thinking about these different bases, it's really helpful to use some sort of notation to indicate that we're working with hexadecimal here. So 4, 2 in hexadecimal corresponds to the letter capital B. So all of the capital letters are counted in that order. Note that there's 26 letters in the alphabet. There's some other miscellaneous characters, and then lowercase letters begin with A at 97. And you might naturally ask yourself the question, why did we do that? Well, let's think about converting 97 into binary. So 97 in binary. Let's do the same thing we did above, right? Just thinking about it in terms of our making change, right? We could use that algorithm, but the making change is actually pretty helpful in this one. Because we think, okay, I couldn't use my 128-cent coin here because that's too big, but I could do a 64-cent coin. So that's 64. I next go down to the 32-cent coin, and 64 plus 32 is 96. So we would have 64 and 32 would get us to 96, and then one more. We already noted that 64 is when we have a 1 in that second decimal, or sorry, excuse me, the second digit in my 8-bit binary number. 32 is represented by having a 1 in the third digit. And then plus 1, so then if we add that up, these are three numbers that are easy to add all together because there's no carrying involved. The letter lowercase a is going to be represented as 0, 1, 1, 0, 0, 0, 0, 1. And now it's convenient to count starting the letter 1 because that's going to indicate that it's the first letter of the alphabet. Same thing as we did right here. So it's the first letter of the alphabet, and this signifier right here tells me that it's the lowercase letter that I'm working with. Okay, well, now if we want to convert this to hexadecimal, again, we can do same sort of math that we did before. In hexadecimal, this first digit, note that if we think about this in decimal for a second, we've got 0, that's worth 2, and that's worth 4, so that's worth 6 all in all. And then this thing here, 0, 0, 0, and 1, so that is 6, 1 in hexadecimal. Let's do the same thing, but for the letter lowercase j. And here we might have to count, in case you haven't memorized which letter of the alphabet j is. Let's see, A, B, C, D, E, F, G, H, I, J. So it's the 10th letter of the alphabet. Noting the thing that we noted up here, we actually have a nice convenient way. So this part here, these 5 digits, are going to count the letters of the alphabet. So if I think about 10 in binary, I could just have this part represent 10 in binary, and this part signifying here is what's going to tell me that's a lowercase letter. So 10 in binary, again, think about it in terms of making change using powers of 2. We could fit 8 and then 2. Again, these are base 10 numbers, by the way, when we're thinking about that, just to be very, very clear here. Well, 8, again, thinking about our binary digits here, right, that represents the 1's place, the 2's place, the 4's place, the 8's place. So that's 1, 0, 0, 0, sorry, 1, 0, 0, 0. And then 2 is represented as 0, 0, 1, 0. If I add those up, again, no carrying that I have to do, it's just 1, 0, 1, 0. So that is what we will have to have as these final digits here. But note, I'm actually going to use 5 digits to store it, so I'll have 0, 1, 1, 0, 1, 0, 1, 0. Another way you could have approached this, if we start counting at 97 here, we'll verify this here. If 97 in binary represents the letter lowercase a, this would also get represented as the value 106 in decimal. Again, remember, you have to be super careful when you're thinking about counting, right? If we start counting at 1, and we want to get 10 past that, or sorry, excuse me, not 10 past that, the letter j is 9 spaces after, right? So if we start counting at 97, the 10th number that we count will be 106. So let's just do a quick double check here, right? Thinking about this in terms of the base expansion, that represents 2, that represents no 4s, 1, 8, no 16s, 132, and 164. So we can go ahead and verify that 106 in decimal would have this representation in binary. Lastly, convert this into hexadecimal. And again, if you like, you can always write this thing with that little subscript 2. I like to chunk it up into little 4-bit chunks just so I can read it better. Thinking about each of these in binary, sorry, excuse me, in hexadecimal, this number 0110, we actually saw it just above here, right? That's 6 in hexadecimal. And 1010 is 10 for the 10th letter. And the 10th letter, when we represent the digit 10 in hexadecimal, it's going to be the letter A. So this will be represented as 6A in hexadecimal. And now, this continues for if we have really any number of letters. So whenever we're using any number of keystrokes, that's going to get translated from the computer using this ASCII table. So let's find the binary and the hexadecimal code for the 2-character word me. And a very, very important thing that we need to note when we are thinking about how this data is stored in a computer is that capital letters are stored differently. They're stored as different numbers than the lowercase letters. So we have to use the process we just established here, right? We first need to think about the letter capital M. Well, M is the 13th letter of the alphabet. So when I'm thinking about counting to that, I'm going to start counting from the letter A. There's multiple ways of doing this, but I want us to think in binary, right? We noted that if we start with a binary number of 010, that's going to give me a capital letter. And the remaining digits are going to be, so it's going to be 1 here, and then 1, 2, 3, 4, so 5 digits. The remaining 5 digits are going to tell me which character it is. So it's going to give me space to count the 26 letters of the alphabet, and there's a few miscellaneous symbols after that. So what I need to do is think about what is 13 in binary. So 13 in binary, again, thinking about it as like making change, I can have 8, and then I can fit in a 4, and then a 1. So thinking about that with my powers of 2, 8 is 1, 0, 0, 0, 4 is 0, 1, 0, 0, and then 1 is 0, 0, 0, 1. So then we'll get 1, 1, 0, 1. So 1, 1, 0, 1 are going to be the last digits here, and again, we're going to put a 0 right there because we could also think about this as being 0, 1, 1, 0, 1. Anytime we're trying to store some number, and we don't actually need to use all the other spaces there, right? We could always just put zeros in front of that, and that won't add anything to the value. So we're going to have this be 0, 1, 1, 0, 1. So this is going to be the letter M. And now we do the same thing, but with the letter E. So E is the 5th letter of the alphabet, but we have to start counting from here, right? So we started counting at 97, which in binary looks like 0, 1, 1, 0, 0, 0, 0, 1. But then we are going to count so that since we started counting here with 1, that represented the first letter, we need to have this part represent 5, and that then in binary will give me a little tail part that I need here. So the fifth letter, if I think about the number 5 in binary, so 5 in base 10 is going to be 4 plus 1, which from what we just noted above will be 0, 1, 0, 1 in base 2. So the letter lowercase e, using the first digits here, starting counting at 97, or I guess you can think about it as this part represents 96, but then the last part tells me which letter of the alphabet it is. So starting with 0, 1, 1, and then the last digits here will have to be 0, and then 0, 1, 0, 1. So then the binary code for the whole thing would be these two things back to back. 0, 1, 0, 0, 1, 1, 0, 1, and then the letter E is 0, 1, 1, 0, 0, 1, 0, 1. Start to go kind of crazy when you talk in binary, it's just ones and zeros. So this, when a computer parses characters here, it is going to parse it in this manner. These 8 bits represent a character, and these 8 bits represent a character. The last thing we'll do here, we can also represent this number using hexadecimal. Remember, each 4-bit string of binary digits converts to 1 hexadecimal digit. Let's remember how to do that. 0, 1, 0, 0. If we think about its decimal numeric value, it's going to be 4, which in hexadecimal is just 4. 1, 1, 0, 1, in decimal, we think about that as 1 plus 4 plus 8, or 13. When we're representing 13 in hexadecimal, remember A is 10, B is 11, C is 12, D is 13. So this will be 4, D, 0, 1, 1, 0, that's worth 0 plus 2 plus 4 is 6, and 6 in hexadecimal is just 6. And then the last digit, 0, 1, 0, 1, again, that's worth 1, that's worth nothing, that's worth 4, so that's 5. So we could represent the 2-character word me using hexadecimal. It would look like 4D65 in base 16. All right, so that's all we have for talking about binary and hexadecimal. We've got one more section that we're going to explore next, in which we're going to look at something a little bit different, but that is still very relevant to mathematics and computing. So I'll see you then.